AWS LoftTalks.
What I'm going to do in my talk here is kind of give an overview of what all this container stuff is and kind of how a lot of folks see the future of infrastructure working, how it's laying out, what are some tools that you can take off the shelf today and use to help build your application, and then mostly just give you an idea of what this infrastructure looks like and what really changes when you introduce the idea of a container. The whole goal here is to create infrastructure that's more focused on applications. You're trying to create an application, and that infrastructure is something that just happens to be in your way. So a lot of what technology is created, things like AWS and OpenStack, and these things are the infrastructure level APIs. The idea of these containers and these clusters is to get us to the point where we're thinking about the application instead of thinking about networking and disk and CPU and I/O. So the inspiration comes from how a lot of these large companies like Google and this paper that Google wrote called The Data Center as a Computer, Twitter, Facebook, Amazon, a lot of these large companies that have a huge internet presence and how they manage the complexity of all this infrastructure that they have to manage in order to actually run their application. The engineers that work at these companies are very effective and efficient because their infrastructure is built in this way that allows them to think about how do I create this infrastructure where I don't think about the individual server, but I think about this whole data center as a computer. This whole thing starts with containers. And so a container kind of changes how we deploy applications onto a Linux server. Generally what happens is we write our application, and in this diagram, this would be like the app.py file. This is like the Python source code to our application. And then everything above it is kind of provided by our operating system. So Red Hat, these things provide package managers so that we can kind of go apt-get install Python, and then we'll just run the app. And so the application and the operating system kind of have this combined effort that they go through in order to actually run the thing. You can get yourself in some pretty tricky situations, though. The underlying operating system is intertwined with our application because we're relying on that exact version of Python. We have Python 2.6 on our laptop and Python 2.7, and we find these little things that act differently between our laptop and our server. What a container does differently is it packages everything together. So instead of relying on the operating system to provide us with Python 2.6, we package the actual application along with our dependencies, along with Python. So you kind of have this little bundle that has everything you need. And the idea here is that we now have independence because we move this little bundle around from a VM that's running one version of Ubuntu to a VM that's running another version of Fedora, and it should more or less work in the same way. And then the final little bit of this container thing is we give it a name, similar to how we have package names like Python 2.6 for our Linux distros. We give our own application a name, and in this example, it's going to be example.com/app. And this is our packaged up final container image. And instead of going through and doing an apt-get install, we rely on a container runtime system. Two container runtime systems are Rocket. So you go like Rocket run the container image, or Docker run the container image. And the basic idea is that would download it off the internet and then get the process actually running on your system. And then you're probably wondering, okay, how do I actually take my application source code and turn it into this container image? It's a fairly straightforward pipeline. You write some code or you write some configuration that takes your code from GitHub, runs it through a CI system. The asset that comes out of that CI system is a single file that is the actual container image. You host that somewhere on a registry, and then you pull that onto your individual servers. And so the idea would be that every time somebody commits code to your application, that you get a runnable asset out of it. And this was something that we kind of started playing with a few years ago. A lot of people wanted to build purpose-built VMs. The problem with a VM, though, is that a VM contains the entire operating system, which is a pretty heavyweight asset to be pulling around. Your entire container might be on the order of megabytes, but an operating system image might be on the order of hundreds of megabytes or even gigabytes. So this asset is something that you can run across various Linux hosts, but is small enough that you can kind of trivially pull it and push it across the internet. We talked about this a bit, but the classic Linux distribution that we use today in the data center to run our apps kind of includes everything, and then the app is this little bit of code that we put on top. And with containers, we kind of change the responsibilities of the distro, which is doing two things. One, it makes it really convenient to move this container image around, but it also creates a problem in that we have a lot of container images with lots of copies of code all over the place. And so we've solved one problem, which is we now have this independent asset. We created another problem that we have lots of independent assets that we have to manage. And so that is one of the complexities introduced by all this container stuff. It doesn't solve all problems for everybody. One very practical problem that it solves is that it makes it very simple for us to be able to have multiple copies of our application running on a single host. A lot of times when you try to do this, where you take version 1 of your application from this morning and version 2 of the application from the afternoon and try to run it on the same host, you're going to run into problems unless you've architected your application well. And so this is a nice way in order to say a few percentage of your traffic on just the latest version of your application, or try out this thing and make sure that it's not consuming too much memory in the infrastructure. These sort of experiments that can be ran on your hosts. The parts in blue here is essentially what CoreOS Linux is. It's a tiny little operating system to make it easy to run these applications that you've built inside of containers. Two popular pieces of technology that you can take off the shelf and use. I'm not suggesting with this container stuff that you have to throw out all your infrastructure wholesale. You can kind of take pieces of it and try it out in your infrastructure today. So the Docker engine is something that you can pretty much apt-get install or yum install onto your hosts, and you can try out one part of your infrastructure inside of a container and see if it works for you. Similarly, our open source container runtime that we built in the last few months, Rocket, you can download onto your hosts, runs in a little binary, and try out building your infrastructure in this way with containers, and try to see if it fits well with how your application is built. The neat thing that we've accomplished by introducing containers is that we have this little asset, this little binary we can move around and run multiple copies on individual hosts. The next thing that we need, though, is we want to have multiple hosts in our infrastructure running this asset, so that if a single VM dies in EC2, or if one of our hosts dies that we have in a rack somewhere, that the application continues running. So there's a few things that we need in order to create kind of a clustered environment. We need cluster configuration. So this covers things like how is the application configured, how is the network configured for the machines within the cluster, where can I find assets, where's the load balancer that I should be putting myself into, this sort of cluster configuration. We need scheduling so that we can say, an engineer or somebody on your operations team can say, I need 10 copies of our backend running inside of our infrastructure, because I know that those 10 copies will be able to handle, the 1,000 requests per second that we get. And so the scheduler is in charge of ensuring that no matter how the infrastructure changes underneath you, that X number of things are actually running. And you need service discovery so that once you get those copies of your application running, you can actually put them behind a load balancer and get your users hitting that traffic. Kind of just walk through a visual example of this. If you're running a single VM and you put your application on there and you have health checking and health monitoring, your application's healthy. And what we're trying to design for here is that your application remains healthy even if that single VM dies, right? So you want to spread the workload over multiple VMs instead. So the machine comes back up, and we realize that having this single VM or this single host running our application is not the best thing to do. So we're going to try to introduce clustering. And so you introduce 4 hosts into your environment, 4 VMs into your environment, and you are able to lose individual hosts. And because we have this active process of a scheduler moving our containers around within the environment based on changes, like a host going down because of hardware failure or somebody accidentally deleted it, the application should remain healthy. And ideally, as we add machines or even more machines, the infrastructure continues to kind of balance out, and it continues to run our application. And as we add more machines and we tweak up how many copies of our application we need running, it kind of load balances itself across the hosts. This sort of infrastructure is how things like Facebook and Twitter are built. They're designed so that the operations side of the house and the engineering side doing the application side of the house are separate things, and they can worry about separate concerns. So we're losing hosts and the application continues to run. The only thing that we're losing when those hosts go away is capacity, RAM and CPU and storage. Configuration is one piece of getting this clustering stuff to work. And I kind of talked through it. You need to configure things like when a container comes up, how does it come up on the network? What IP addresses does it get? What ports does it allocate? You need application configuration, like where are the certificates that this application will need? Where's the configuration for when it adds itself to a load balancer? This sort of application-specific stuff. And then finally, you'll want to add the application actually into a load balancer so that traffic comes to those processes and serves up your app. And then the final piece of this configuration is scheduling, which is where does the actual process land in the host? And so we've built an open source tool that helps you have a cluster-wide view of this sort of configuration. It's called etcd. And as one example here, we have a tool that makes it easy for you to configure the network for all these containers. And so you kind of define what the network looks like, and the containers draw out of this network pool. Another piece is load balancing. So there's a load balancer that's built where you add in backends. So in this example, you're adding in a backend for something that's running on this host on localhost, and that'll get load balanced across all the applications that are in this backend. All these things kind of go through etcd, and the property that etcd gives you is a place to store configuration that is across all of your hosts. And then the other piece of this is what does scheduling and service discovery look like, and how does that actually work? So the APIs for this scheduler system is pretty straightforward and is very centered around you, the person trying to get work done. And basically what you do is you would say, we'll take this example.com/app thing that we built earlier, this runnable asset, and you as the user put in your intent, and your intent will be like, I want 10 copies of this running. And you tell the scheduler API, run 10 of these things. The scheduler is a simple piece of software that sits there and looks at all the machines that you've added to your infrastructure and figures out where would be the best place to run that container, run that process. And it's in charge of placing it on the machine. And it also is sitting there in this constant loop saying, well, has the infrastructure changed? For example, the user asked for 10. I go through the inventory of our entire infrastructure. I see only 9 are running. All right, I need to schedule one more of them. And it's this very active process. It's something like a thermostat. You know, you set your thermostat to 72. Your thermostat knows that it's currently 68 in the house. So I'm going to have to start driving the furnace upwards. And at some point, it stops. And it's like, all right, everything's at 72. I'm going to shut off the furnace. And it's just an active control loop. And so the scheduler essentially has an idea of the entire infrastructure and then the user's intent of what applications they want running. And it kind of handles the rest and makes sure that the infrastructure matches what the users requested. In this example, the user's intent is that they'd like 2 copies of application version 1 running. And so the scheduler places those 2 copies on one of the 8 machines in the infrastructure. Sometime later, another user says, I'd like version 2. Again, I'd like 2 copies of it somewhere within our infrastructure. And then at some later point, somebody says, I want version 3, and I'd like 3 copies of those in the infrastructure. And then 2 of the hosts die for whatever reason. There was somebody messed up and deleted the VMs, or there's a power outage or a network partition. And the scheduler is there watching for those sorts of changes and reschedules things that were intended to be running on other hosts, taking into account resource constraints, whether there's enough disk and CPU and memory in order to actually schedule that job. So scheduling, there's a few different open source projects that can be used to do this scheduling component of infrastructure. One of them is Fleet, which is a very simple scheduler that we've built. It acts something like an init system. So you describe your job, you say Fleet CTL start, and that job starts up on one of the machines in your infrastructure. It uses pretty simple configuration tools and is pretty dumb overall, but it's a very easy way to get started with these sort of scheduling systems. A more sophisticated one is coming out of Google. It's an open source project that can be ran on any cloud infrastructure, and it provides a very similar API where you say, I'd like to have these things running, and it runs it, but it also takes care of things like service discovery and load balancing so that you're not responsible for that complexity, because the scheduler knows where things are running. It's in a very good position to figure out how to add those running processes into a load balancer. Another open source scheduler that's been very popular is Mesos. Mesos' biggest user is Twitter, and Mesos' project has focused a lot on how do I get the most efficient usage of my infrastructure. So how do I get the most bang for my buck when I buy those VMs? I want to make sure that they're fully loaded and that I'm utilizing all the disk and CPU and RAM that I'm paying for. And so it does a process of bin packing to ensure that when you buy a piece of infrastructure, it's going to be utilized as efficiently as possible. I've kind of ran through the major parts of this application-focused infrastructure. It really begins with the container. The container is the thing that allows us to move the workloads around and kind of have this independence where we're not having to rely on explicit human configuration to decide how our infrastructure is laid out. What I'd recommend people who are interested and intrigued by all this technology, the first thing I would do is try to get my application running inside of a container runtime system like Docker or Rocket, and try out whether it makes deploying your code better, and whether it frees up your team from some of the operational complexities of managing version 1 and version 2 and version 3 of your application, and version 1 and version 2 and version 3 of your infrastructure, installing all those packages and the configuration of those hosts. After you have that running and it's solved a handful of problems for you, the next thing that I'd suggest is that you start to understand what are your application's needs around service discovery or load balancing. Some people have very simple needs. It's a simple Ruby on Rails application, and you only have 1 or 2 processes involved in that. And you just want to be able to do simple experiments like, say, I want 5% of my load going to this new version of the application. But kind of map out what are your actual requirements for your application today, and what are the pieces of technology that'd be helpful to fix those problems that you're having. And then after you have figured out your service discovery and load balancing needs, start to play with these schedule-based systems. Because as your application grows, you're going to end up buying more infrastructure, buying more VMs, and it's going to be harder and harder to manage that inventory. And so having a piece of software that's going to help you manage that inventory will be very helpful and free up your engineers and operations people to do more important things. Finally, enjoy the benefits of having an app-focused infrastructure. You're kind of freed up yourself from a lot of this complexity of thinking about explicitly how to configure and run these complicated pieces of technology.
AWS LoftTalks.